graduated in 2017 in mechanical engineering and went from there to wood group. He's been working with the wood group in vibration and noise suppression group since that time. Some of you would remember the predecessor of that group was beta monitors and beta machine group. Austin started his career with them in the design group, and then he's moved into the field. So he's traveling all over North America, troubleshooting vibration problems. I'm going to share some of them with us tonight. So welcome, Austin.
Thank you.
The floor is yours.
All right, just making sure that. Just making sure you can all see this properly. Close this. Okay, hopefully this should be working. There we go. All right, well, thank you everyone for joining us here tonight. I appreciate you guys pushing this back by 1 week for me. Last week, I was up in Grand Prairie doing some troubleshooting on a screw compressor, which was also experiencing some shell mechanical natural frequencies. So it was a bit of an odd coincidence with that. The title of this presentation is Shell MNFs and Transverse ANFs. MNF refers to mechanical natural frequency, and ANF refers to acoustic natural frequency. My background is, or at least what I do at work, is primarily dealing with rotating and reciprocating machinery. And the purpose of this presentation is to kind of show you some of the more exotic or unusual phenomena that can happen on some of these machines. But before we do that, I'm going to give you guys a quick crash course on reciprocating compressors because they can be, some people might be a bit unfamiliar with them. I'll give you a brief overview of the basic design of reciprocating compressors, the sources of acoustic pulsations and vibrations in these systems, and some of the methods that we would use to mitigate these forces, either at the design stage or after it's been built and it's already vibrating in the field. But the meat of the presentation will be a case study of a unit that had some inadequate pulsation control. And I'm going to show you what I saw in the field, how I diagnosed the specific problem in the field, and some kind of lessons that we learned from it internally and good things to note. But before we get into that, this is a reciprocating compressor. For some of you, it might be the first time you've seen one. So we're going to go through some of the basic principles. And what these machines do is they're kind of like the inverse of an internal combustion engine. Whereas with an internal combustion engine, you have a fluid that is doing work and a piston to produce movement. With this, you have the exact opposite. You have a crankshaft that is doing work and a piston to do work on the gas, to compress it and either push it down a pipeline or supply it to a reactor. In Alberta, it's mostly pipelines, I suppose. So we're going to start with the components at the upstream part of the gas flow and move our way downstream as it passes through the machine. This tall vessel on the right is the scrubber. It removes entrained liquids in the process stream. Liquids being incompressible can damage the cylinder when it attempts to compress it. The vessel on top, you see, that's oriented horizontally is what's called a suction bottle or a suction pulsation damper. And as I'll show you shortly, the cylinders will output pulsations into the system. And the purpose of this vessel is to serve as a filter so that these acoustic pulsations don't travel through the vessel downstream and cause some nasty shaking forces away from the unit. These in the center are your compression cylinders, and these compress the gas, as you would hope, but they also introduce pulsations into the system through the reciprocating motion of the cylinder. The discharge bottle on the bottom, it also helps to reduce the pressure pulsations from the cylinders moving into the discharge system. Not shown in this picture is a gas cooler. It's outside of the building in this picture. And of course, as you compress the gas, you heat it up. PV equals nRT after all. And you want to keep that gas temperature under control to prevent damage to the metal and all the seals in the compressor. Compressors are often multi-stage for this reason. You compress it in one stage, you cool it, and then you compress it in the second stage to avoid overcompression in one stage of compression. So how and why do these things shake and vibrate? There are two kind of different categories by which these machines can produce vibrations. The first is mechanical. The thing is moving. You have your gas rod forces. When the compression cylinder moves back and forth, it will exert a force on the gas rod acting on the crankshaft. These forces bear the brunt of the compression of the gas, and they can be significant, going right up to your rated rod load. For a large unit, that might be 100,000 pounds force, so quite significant amount of force. And this vibration will occur primarily synchronized with the movement of the cylinder. There can also be rotating and reciprocating motion. So your crankshaft can have an inherent imbalance to it. You would, of course, try and design away as most of that as you can, but there will always be a little bit of residual imbalance that can cause shaking in the system. The reciprocating motion of the pistons can also cause a force couple. The unit I showed in the picture earlier it has 4 throws in it, with 2 being opposed to each other on each side. And when you get the cylinders moving phased 180 degrees apart from each other, that can cause a couple, which can induce a rotating motion on the frame. There's also the engine forces. Engine drivers are pretty notorious for shaking pretty bad. Electric motors, not so much. But you can imagine that with all those little explosions going on, it can cause some pretty bad vibrations. The key thing to remember about mechanical induced vibrations is that they are inherent to the operation of the compressor. There's not a whole lot you can do design around these. You can, try and balance the crankshaft a little bit better, but you're never going to do anything about the shaking forces on an engine or the gas rod forces. These are also typically localized to the compressor frame. They won't be transmitted down the piping because it's just the physical transmission through the metal. The other, and I would say a little bit more interesting one with reciprocating compressors, are the acoustically induced vibrations. These are caused by the pressure pulsations emanating from the cylinders, and they primarily travel as longitudinal waves throughout the system. Longitudinal meaning the pressure differential travels in the same direction as the flow of the gas. If you can imagine that if you have an end of the piping, like by an elbow or a pipe cap, the pressure will act on the pipe to produce a force. Now, the static force is easy to see, but when you have dynamic pulsations, you will have dynamic forces acting on these ends of the piping and the bottles and the vessels. And if one end is at a pressure maximum and the other end is at a pressure minimum, you will have a force differential between those 2 ends of the pipe. This causes an imbalanced force, which makes the pipe shake. There are also some other phenomena that can cause this. We can talk a little bit more about that later, but it is overwhelmingly the reciprocating motion of the compressors that will cause acoustically induced vibrations in this system. The important thing to remember with these acoustic vibrations is that we can reduce the amplitude of these through proper acoustic design. And if we don't, they will propagate throughout the piping, and they can travel hundreds and hundreds of feet throughout the system. We have machines where you have a compressor building, and then on the opposite end of the plant, you have some little appendage shaking somewhere from this machine 200-300 feet away. They can propagate for a very long ways. The other very interesting thing to note about these forces is that the peak frequencies will occur at integer orders of operating speed. So if you have a compressor operating at 600 RPM, your fundamental frequency is 600 RPM or 10 hertz, 600 divided by 60. But you will also see residual forces at 20 hertz, 30 hertz, 40 hertz, and so on. And the origins of these forces can be useful for helping to diagnose different problems, depending on what frequency you measure on the machine. Yes.
They're not seeing the full screen. I think you can control just expand. We're seeing
Are you seeing the presenter's view on it? I am not sure.
If it's difficult, don't worry. We can still see it. It's just
I'm not quite sure how to resolve this. It seems, yeah. Okay, yeah. Okay, yeah. Sorry about that, guys. I'm not quite sure how to fix that. But so for the origins of specific frequencies, 1 times operating speed is pretty obvious. If you have a machine reciprocating at 15 hertz, you're going to get stuff vibrating at 15 hertz. That much is clear. But at different multiples of that, it can get a little bit more convoluted. So multiples at 2 times, 3 times, 4 times, and above are caused by the interaction of gas as it's pushed by the cylinder face through the valves. If you can imagine, the reciprocating motion of a compressor can be described as a sine wave. And so the movement of the gas from the compressor through the valves as it either sucked into the cylinder or discharged to the other side can too be described as a sinusoidal motion. But of course, it's not a perfect sine wave. You have gas dynamics, the compressibility of the gas, how much resistance that the valves will impart on the system. So you're going to end up with an imperfect sine wave. How do we describe this imperfect distorted sine wave? Well, we can describe its components through a Fourier decomposition. And this isn't just some mathematical trick. The Fourier components that you will get out of this distorted sine wave are what we would call the pulsation coefficients in the system. So that is the origin of how you can get a machine that operates at 15 hertz getting vibrations at 45 or 60 or 75 hertz. Your typical reciprocating compressor will operate from 300 RPM, which is one of those old school integral machines, your Worthingtons, your Cooper Bessemers, for those who have dealt with those, right up to about 1800 RPM for higher speed aerial machines. So that'll be a fundamental frequency of about 5 to 30 hertz. In general, it's rare to see frequencies above 10 times operating speed or about 150 hertz. If you see something above that, you have something strange going on. These forces can additionally be amplified by either acoustic or mechanical resonances in your system. Hoping to get to the next slide here. There we go. So for resonances, for an acoustical resonance, what we're looking for is a standing wave between 2 closed or open ends of the piping system. So when I would look at this, I would see a risk that there could be a standing wave between the 2 ends of that horizontal bottle. There could be one from the cylinder nozzle in that right up to the bottom of the bottle. That short little span there could get a high frequency resonance. There could be something in the scrubber vertical direction between the top and bottom of that vessel. There could also be something in what's called a dead leg. And a dead leg is a kind of piping where there is no net flow going through the pipe. You can imagine if there's a little short stubby piece in the pipe that was used for, say, a pressure sensor or a vent or a drain, and there's gas flow moving across it. It's kind of like blowing across a Coke bottle. You can get that kind of resonance coming across in the system acoustically. Mechanically, for the actual shaking of the machine, you might see a bottle cantilever mode. where the bottle flexes kind of into and out of the page on those nozzles. You could get a cylinder vertical mode, and you can see in this image, there are some A-frame supports underneath the cylinders to try and prevent that motion. You could get vertical forces developing in the scrubber. You could get a piping lateral mode where it flexes in between supports. The point I'm trying to get across is that there are dozens of different combinations where something in this system could be resonant. And with all the different variety of frequencies you can get, these are very high risk machines for having high vibrations. I think my mouse might be dead, unfortunately. I have to press this. So how do we control these pulsations? The easiest possible way to do that is something that's called a restrictive orifice plate. We can see a diagram of it here on the right. These orifice plates are put into flanges, which I've highlighted in the picture. And what they do is they induce turbulence and pressure drop in the gas flow. This turbulence and pressure drop helps to disrupt the standing waves that occur in the piping system and prevent the acoustic resonances from amplifying pulsations. These orifice plates they're cheap to implement. The only real cost you have is that the pressure drop they induce means the compressor has to work a little bit harder to push that gas through it. But the more effective way to do it is with something called the bottles, and those are the horizontal vessels I talked about earlier. The primary thing you're looking for with the bottles is the addition of volume to the system. Volume will add damping at all frequencies, but there's a trade-off to it. When you build one of these large vessels, they have large cross-sectional areas as well, and force is equal to pressure times area. So if you have a very large cross-sectional area, you create a risk of having high shaking forces on the bottle itself. So the way we can design around that is by welding an internal baffle in the middle of the bottle. And the function of this baffle is identical to that of a very large orifice plate. You try to break up the standing wave inside of the vessel before it can resonate and be ejected out into the rest of the piping system. But sometimes this isn't enough to control pulsations. If you have a very powerful machine, you have to do something called acoustic filtering. So acoustic filtering is typically accomplished through something like a Helmholtz filter, where you have the section of the bottle sectioned off with baffles, for which gas cannot flow through. And instead, the gas will pass through these narrow choke tubes between sections of the vessel. And this creates a filtering system that's kind of analogous to an electric low-pass filter. And I would highlight the term analogous specifically because back before digital computing was a thing, these systems would be modeled with electrical analog computers. And you would model the resistances and the impedances as if they were a physical system. So it's a kind of a bit of a cool history of computing. Beta Machinery Analysis was actually the first company to figure out a way to model this digitally. So that's kind of our claim to fame on that one. So how do we actually model this beforehand? And this is kind of what I would do in the old division I worked in. So on the left-hand side, we have an example of an acoustic model, and this is used to predict the pulsations in the system before we actually build it. You can see here that in this image, we're predicting a resonance on one of the dead legs. So there's a closed valve at the end of that red area, and on that closed face, pulsations will be reflected backwards, and they'll cause a resonance in the system, which can amplify the shaking forces. On the right-hand side, we have an example of a different system, and it's a mechanical model that's been made in ANSYS. And it shows a predicted mechanical resonance that's occurring on a scrubber in the system. One thing I would note that maybe those who can, with a keen eye, can see is that if you've ever looked at an ANSYS model before, you'll see a lot of patchwork of different nodes on it as the 3D, the finite elements are generated. But this one looks like just a series of hoops or cylinders that are joined together. That's because these are both one-dimensional models. So we're not actually modeling the 3D behavior of the system, we're parameterizing it. This is a huge strength for reducing the solving time of these systems. I mean, a complicated system, even with modern computers, could take a day to solve. But there are weaknesses to it in that you cannot model certain 3D behaviors. That's something to make note of later in this presentation. So with all that, yes.
Response that you would get counting of the cylinder, you would be able to get that definition.
Yes, yeah, that's the movement of the whole system predicted at that frequency. So you might get the cylinders acting up at a different frequency, right? So there goes your 15-minute crash course on reciprocating compressor design. Hopefully you managed to absorb all of that, because now I'm going to throw at you a system that behaves in a little bit more complicated manner than that. So this happened, I want to say about 9 months ago. And we were called out to do some work on a compressor that had been installed 20 years ago, and it had been acting up the entire time. There were repeated failures on SBCs, which is our term for a small bore connection, little thermowells, pressure sensors sticking out of the pipe, those tiny little twigs that could snap off pretty easily. There have been broken pipe supports in this one and a lot more issues. So you can see the 2 compression cylinders in the foreground, but there are 2 more opposed to them in the background for a total of 4 cylinders. And this particular unit was taking natural gas from about 100 PSI on section to about 300 PSI on discharge. It's a variable speed engine driving it, so it could go from 600 to 900 RPM, or about 10 to 15 hertz, if speaking in terms of frequency. And it'll develop around 1200 horsepower. All things considered, this is a very average unit. However, the bottles were empty, there were no baffles, there were no choke tubes, and there was not a single orifice plate on this unit. This is not best industry practice. This might be acceptable for something with 100 horsepower, not for something with 1,000 horsepower. This is by far the most powerful machine I have seen without these sort of pulsation control systems. And it's so unusual that it created some phenomena that the old guys at Wood, who had been there for 50 years, had never seen on a reciprocating compressor before. So the gist of the complaint we got from the customer is that this thing was making a funny noise. For those of you who have ever been around these units, they are incredibly loud. It's double hearing protection all the way, but it's your typical machinery noise. It's not a pretty sound to look at, or hear rather. This one, on the other hand, it was much more musical. It was making this wonderful orchestral sound coming from its bottle. It's not something that you would expect from this. And some kind of preliminary measurements that were taken before I got there showed that there were high vibrations on the suction bottle up top at about 200 or 208 hertz, or about 14 times run speed. Now, we've talked about 1 times, 2 times, 3 times earlier. We did not talk about 14 times. And we certainly did not discuss any phenomena up to 208 hertz. This is very high frequency for this type of unit. Vibrations were highest in the middle of the bottle, kind of in between the 2 cylinder nozzles. So it's very interesting when you go up there and you touch it for yourself. You'll touch the end of the bottle and it's quiet, it's quite still. You glide your hand around along it, and by the time you get to the middle of it, you're vibrating off of it. You can barely keep your hand on there. So, and what we also found is that this was extremely sensitive to unit operating speed. Now, as you can imagine, as you shift through the range of 600 to 900 RPM in this machine, you're going to start exciting different frequencies and different resonances. But you don't need to be bang on something. If you have a resonance at 800 RPM, you'll pick up a little bit at 775, a little bit at 825. Not this one though. It peaked at 893 RPM and exactly 893 RPM. 890, it was fine. Don't worry about it. So this highly unusual behavior is characteristic of what is known as a shell mode. Earlier on, when I showed that animation of the scrubber swaying from side to side, that's what I would call a translational mode. You have something that's moving, but it's not, its cross-section remains constant. At higher frequencies, you can have phenomena where the cross-section of a vessel is actually deforming. If you can imagine kind of a balloon bulging in and out or a hula hoop being stretched. It's quite fascinating to think that's something as rigid as an inch-thick steel shell can deform by that much. But at the bottom here, we can kind of see some diagrams of that. The first one you see is kind of like a breathing mode where you can imagine the diameter kind of increasing and decreasing uniformly. And by the time we get to something like n=1 or the n=2 modes, you're going to start to see some nodes appearing in the system where you have different ripples going across that cross section. So before I go out into the field, I usually try to toss something in the ANSYS to see what's going on. I don't like going in blind, especially in something like a shell mode. So I got the schematics from the customer and I put it into ANSYS. And what ANSYS predicted for me is a shell mode occurring at 208 Hertz. Okay, so we have a likely culprit. And you can see in this diagram here, you can see locations of maximum vibration are kind of interspersed with locations of minimum vibration about 45 degrees apart around the circumference of this vessel. One thing I would note about this diagram is it differs from the previous animation I showed you in that this is a 3D model. You can see the kind of checkerboard pattern of those finite elements in the system. So this model is capable of predicting 3D phenomena. As an aside, I was, as I said, dealing with a screw compressor in Grand Prairie last week. And one of the things that happen on screw compressors a lot is very, very, very high frequency, complicated shell modes. And this here is an example of what another one can look like. So it's not that simple kind of just flexing that we saw in the previous image. You can see there's a dozen different nodes spaced all around the circumference of this vessel, all spaced so finely you almost can't even see them. Some of you in the back might have to squint. And you can see there's kind of a variety of shapes you can do. And the one on the left, it's kind of like big lines going across from the top and the bottom. And the one on the right, it's more like different patches, like it kind of looks like almost polka dots across the vessel. So you can get some very, very complicated deformations that occur with these shell modes. So with that being said, the shell mode on the suction bottle was not the only problem with this unit. So we had the hum that was going on the suction bottle. We also had another phenomena going on the discharge system. The entirety of piping, everything from the pipe to the pressure relief devices right up to the cooler, had these extremely, extremely high frequency vibrations, even higher than 200 Hertz. And it was endemic throughout the system, in contrast to the suction bottle, which was a localized problem. There were also several broken pipe supports all throughout the discharge system. And it's a bit of a chicken and egg situation. Do you have high vibrations because you have broken pipe supports? Or do you have broken pipe supports because you have high vibrations? And you can get a pretty nasty feedback loop with that going on. Also, the entire left-hand side of this compressor, from the scrubber to the cylinders to the piping to the bottles, it was all kind of moving back and forth in this image, all at the same frequency, all with the same phasing going left to right. Very, very unusual to see all of that moving at once. And just for a quick clarification, when I say high vibrations, our guideline is about 1 inch per second. So when you see something like the pressure sensor at the top of the suction bottle moving at 8 inches per second, you get a little worried that it's going to snap off. Yeah, well, I've seen it. I had to get up close and personal with these ones. Oh yeah, yeah, got to put your sensors on it. So I had some pretty strong qualitative evidence that there's a shell mode. I had some predictions from ANSYS that there was a shell mode. How do I prove it? So for vibration testing, I would argue it's pretty straightforward. You place vibration sensors all around the circumference of the pipe, and if you plot them and look at their phasing, you can see exactly how the pipe is deforming. Here's an example of a bit of a plot that I made, and these are the actual measurements from this system, and you can very clearly see that same shape that we were predicting in that ANSYS model. But what about for MNF testing? So for mechanical natural frequencies, you could have high vibrations at a mechanical resonance, but you can also have high vibrations outside of a mechanical resonance. If you remember kind of your spring theory, force is equal to your spring stiffness constant times your displacement. But if you think about that in terms of dynamic forces and you think of force and stiffness as functions of frequency, what can happen is that what a mechanical resonance is basically when at a certain frequency, there's not a lot of stiffness. So you can have a pipe vibrating with very high vibrations with not very much force if you're at a mechanical resonance because the dynamic stiffness is so low. On the other hand, if you can have a huge amount of force in the system, but not very much vibrations if you're not at a mechanical resonance. If you have a situation where you have high vibrations and you're not at a mechanical resonance, that's extremely bad because you must have extremely high forces to produce that if it's also extremely stiff. So the reason why we want to also test for MNFs is to see, okay, is there something that's some mechanical phenomena that is making this system worse? So we're going to do a bit of an exercise in how you would test this, or how I did test this in the field. I want you to consider a vessel with 3 relevant mechanical natural frequencies, 2 lateral or translational modes. So you can imagine that bottle moving in its entirety from left to right, or moving in its entirety from up and down. But this bottle, let's say, will also have a shell mode where there's no net translational movement left to right or up or down. It's just a deformation of that shell. How do we tell them apart? So what we're going to do is place 3 sensors on this shell, spaced 45 degrees apart, horizontal, diagonal, and vertical. And we're going to conduct 3 bump tests. What I mean by a bump test, you might have also heard it known as an impact test or a ring down test, is you smack it with a hammer and you measure the frequency it vibrates at. And it's a prop. And the reason why this occurs is when you smack something with a hammer, you're introducing force at a whole, it's broadband force, a variety of frequencies. So if you go and touch a crystal glass, it doesn't matter. You don't have to hit it in a specific way. It'll always make the same sound. You pluck a guitar string, there's no technique to plucking it. It just makes the sound because it wants to vibrate at its natural frequency. So we're going to conduct bump tests in 3 different directions, basically in line with each of these 3 sensors. We're going to measure the response, and we're going to see how we can tell a shell mode apart from a translational mode. So first, let's look at the lateral or translational modes. These are very intuitive. If we were to strike in the vertical direction, we're going to pick up a response on the vertical sensor. We're not going to pick up a response on the sensor placed horizontally because it's orthogonal to the strike. We wouldn't expect it to move very much. There might be some bit of rotation going on, but the amplitude would be very minimal. On the diagonal sensor, sensor B, we're going to get 0.707 times the response, square root of 2, because we're at 45 degrees. If we repeat the test, this time in the horizontal direction, we're going to get the same thing, but rotated by 90 degrees. Your horizontal sensor will be excited. Your vertical sensor will not be excited. Finally, if we strike in the diagonal direction, you're going to get all three sensors kind of excited. Your vertical MNF will get a partial degree of excitation in sensor A. Your horizontal MNF will get a little bit of excitation in sensor C, and sensor B in the middle will be picking up a little bit of both frequencies. So let's now test what we would expect on a shell mode. And in this kind of image, the kind of purple crosses there, those are going to be our presumed vibratory nodes. So locations where there's minimal vibration on the shell mode. If we were to strike in the vertical direction, we would pick up a full response on sensor A at the shell mode. But we would also pick up a full response on sensor C at the shell mode, because shell modes are radially symmetric. However, we wouldn't pick up any response on sensor B at all, because it's put on one of the vibratory nodes. If we repeat the test, this time in the horizontal direction, we get the exact same result because of the radial symmetry. If we strike, however, along a node on the shell, none of the three sensors are going to pick up any response at the shell mode frequency, because you're trying to excite a location where it is dynamically stiff at that frequency. So here's some real data that I measured from the field. I put sensors all around it and hit it and measured the response simultaneously. And you can see on the left-hand side, we see a very pronounced response at 209 hertz. And this response is being measured on two sensors, the horizontal one and the vertical one, but there's no response being measured on that diagonal sensor, which you can kind of see with the red line below. This is what we expect from a shell mode. In the figure on the right-hand side of the screen, all that I did is I used my hammer and struck it at 45-degree difference from the first hit. And suddenly, we don't get hardly any response at all at 209 hertz on any of the three sensors. You can kind of see that other modes are excited. When I rotated that sensor, I suddenly got a mode at about, 45 or so hertz in the right-hand side of the screen. So you can see how those translational modes are affected by this as well. Just a bit of an aside on instrumentation. When I say hit it with a hammer, I really do mean it's a hammer, but it's a special one. It's an instrumented hammer. And what it serves two purposes. The first is to serve as a trigger to tell when the analyzer to start recording the response. The second is there's a force transducer inside of it. So we can measure how much force that I am imparting onto the system at each frequency, so that when I measure the response, we can plot that against how much vibration per unit force will occur. This picture on the right-hand side is from my recent trip to Grand Prairie, and you can see an example of how I would test the vibrations on the machine while it's operating. And there's sensors going all the way around it on that one. So while I was testing this, our typical testing methodology is to typically do what's called a baseline test. I'll put sensors all around the system, see where the problem areas are, and then I'll analyze the data. I'll come back to where there are high vibrations and do some very thorough testing on the parts of the system that are bad. So I went through all those motions with the suction bottle and the shell mode, feeling really good about myself that I figured it out. And as I was up at the control panel, moving down the speed of the machine, which operators sometimes let you do yourself, sometimes they don't like you touching it, I heard another strange hum coming from it. And just by ear, you can tell, oh, this is a different pitch than the other one. What's going on now? So what you kind of have to do is I set the machine at the speed, and I just went around through this whole plant trying to figure out, okay, Where is it coming from? And I eventually figured out that it was coming from the discharge bottle right beneath the suction bottle. This sound, it was fainter, it was a little hard to find, but it was really high pitched. And it was also extremely sensitive to that run speed. So I'm thinking, great, I have another shell mode. And here's just an example of some of the vibration data we took from it. You can see we have frequencies at about 420 hertz and another one at about 690 hertz. We have strayed very far away from the 15 hertz that we talked about at the beginning of this presentation. I think, in fact, this might be a record frequency for this sort of phenomena that I've seen personally. So I repeated the same testing I did for a shell mode on the suction bottle, but I found absolutely no evidence of it on the discharge bottle. However, I did note that for the suction bottle, it was a localized resonance. The suction piping upstream, it was totally fine. On the discharge bottle, though, these 400 and 600 hertz frequencies propagated throughout the entire system. So from the beginning of the presentation, when we see propagation of forces, we expect acoustical phenomena at play. And that is indeed what was occurring here. This was being caused by what's known as a transverse acoustic natural frequency. Earlier, we talked about longitudinal waves, where the pressure pulsations travel downstream in the pipe along with the gas flow. So with a transverse wave, it means the pressure pulsations are occurring orthogonally to the direction of gas flow. So you can imagine the gas kind of pulsing like a balloon being inflated and deflated inside of the vessel. And you can kind of see kind of cross-sectional diagrams of what some of these mode shapes might look like here. These are common on high-speed screw compressors, but they're very rare in reciprocating compressors. Reason being that reciprocating compressors are typically lower speed, and these phenomena typically occur at very high frequencies. Reciprocating compressors also typically have pulsation control mechanisms, which would prevent these from ever occurring in the first place. But as we know, this did not happen when this system was built. Here's just a better kind of picture of some transverse waveforms that I got from an old textbook. You can see the plane wave is an example of the longitudinal wave. And this kind of cross-section, you can imagine pushing its way throughout a pipe. But with the other transverse mode shapes, you can see how that plane is being deformed in 3 dimensions. And I think in this case of what we were looking at in this system, we were getting an annular mode on that bottle. So we have spreadsheets that we can use to calculate predicted acoustic natural frequencies. And the first 2 predicted ANFs were at 420 hertz and 690 hertz, which is exactly what we measured on the discharge bottle. What we reasoned is that the lack of orifice plates on the system on the cylinder nozzles caused high broadband energy to be ejected from the cylinder directly into the discharge bottle. Because when that cylinder is moving back and forth, as we said before, you'll get stuff at 1 times, 2 times, 3 times, and so on. But yes, it can go all the way up to 60 times. It's just typically that you would almost never have that because these orifice plates are so lethal to high frequency pulsations, incredibly effective. But when you don't have them, well, this is what you get. We reasoned that once in the bottle, the bottle acted as a resonator, amplifying the pulsations and shooting them out into the rest of the discharge system of the unit. The bottle itself wasn't mechanically resonant, which is why I didn't pick up high vibrations on it during baseline testing. I only caught it because of that high frequency noise that I heard. In addition to all of this, the pipe was really, really poorly supported. I'll show you some pictures of that later of what bad pipe supports look like. So the question is, can an acoustic phenomena also explain what was happening on the suction bottle? These transverse acoustic resonances are a very common excitation source for the shell modes that we saw on the suction bottle. However, when I went and calculated it, the first predicted acoustic natural frequency was pretty far off, about closer to 300 hertz than 200 hertz. And that's a sufficient separation margin that you're not going to expect to see any amplification. Moreover, other areas of the suction system, as I said, did not have high vibrations at either 208 hertz nor 290 hertz. So I was pretty confident that there wasn't an acoustic phenomena going on in the suction system. So if it wasn't caused by acoustic forces, it was probably being caused by mechanical forces. And I reasoned that some cylinder stretch would have been, would be my first guess on that. So here are some examples of some of those bad pipe supports I was talking about earlier. You can see on the left, they've made some holes for some anchor bolts in the beam, but they didn't actually put in any anchor bolts. On the right-hand side, yes, the beam is levitating off of the concrete. Your dynamic stiffness is 0 at all frequencies. Cracked pipe support. You got to get a lot of force to crack steel like that. And you can see one of the attempted repairs on the right. So they're just desperately trying to hold down this thing and not doing a very good job. But there was another problem in the whole system that I talked about earlier, how the entire left-hand side of the unit, from the scrubbers to the bottles to the cylinders, every bit of it is moving from side to side in the same direction at the same frequency. Sometimes these vibrations were resonant. There were some resonances in the piping here and there, but most of the time they weren't. That scrubber was not resonant at the frequency of, 84 hertz or so. Neither were the cylinders, nor were the bottles. So we have a different phenomena going on here, and it's endemic to the entire system. 84 hertz corresponds to about 6 times operating speed. So that's kind of in the ballpark with what we would typically see on a compressor. There's nothing exotic going on here. There's just a lot of force. What we found was what's called a bottle half wave resonance. Earlier, I talked about how you could get an acoustic resonance, a longitudinal resonance occurring in between the two ends of that bottle. Well, here's an example of it. So these are some plots from our design team, and this is from the software we used to actually model the system afterwards. And in the left-hand side, you can see some of the predicted shaking forces on the suction bottle. And and the y-axis there goes up to about 1,800 pounds of force at 84 hertz. The red line there is our guideline for reference. So this is about 2.5 times what we would consider a safe level for this unit. On the right-hand side, we can see the discharge bottle, and it's up at about 5,000 or 6,000 pounds of force. So about 10 times what we would consider an acceptable shaking force level. This is a disastrous amount of force that you could have in the system. And this is all occurring because, as I said before, those bottles were completely empty. There's no baffle inside of it to break up that resonance. What we reasoned was happening is, you can imagine both of the suction and discharge bottle, they're facing in the same direction. And when you have those forces lining up in phase on both the top of the cylinders and the bottom of the cylinders, it just drags the whole compressor across when you have so many thousands of pounds of force acting on the unit. The real risk of that, by the way, your failure points are typically shearing on the cylinder nozzles. For those of you who have ever seen these vessels before, there's a reinforcing pad around the vessel nozzles to make up for the material that's lost from the nozzle connection. Those connections, they're very vulnerable to high stresses, because if you can imagine the bottle moving left and right, your thinnest portion of it is those nozzles. So cracks on those nozzles is a very common problem when you see phenomena like this. The final area that we were seeing high problems in were the small bore connections. And what I mean by small bore connections is anything that's pipe size 2 inches or less. Pressure sensors, thermal wells, vents, drains. Anyone who's worked in a chemical plant before knows how much of a headache these things can be. We have entire scopes of work where we go out to an oil refinery and we perform vibration assessments on every one of the small bore connections in an oil refinery. So 10, 20, or 30,000 of these things that we look at, just having, I don't know, 5, 6 guys rotate there out of the plant for the better part of a year. These are a huge headache. And the reason why is because they're usually poorly supported. They're just sticking out the end of the pipe. And they're vulnerable to a huge range of frequencies. And they're really small, so they can't take a lot of stress. So in this system where there's no pulsation control at all of these little appendages are vibrating everywhere. And they actually cracked quite a few of them before I got there, which is, it's quite serious because a crack is a breach of containment and the process fluid is natural gas. So there's an explosion that you're dealing with right there. So to give you an idea of how high vibrations were, these miniature accelerometers we use. And the reason why we use small sensors on these is because if you use a big magnet mounted sensor, you're adding a lot of mass to a small connection. You're going to detune it. You're going to change its natural frequency. So we use these little glue-on sensors you can see in the image on the right. And these sensors are good up to about 50 Gs of acceleration. Beyond that, the sensors start to overrange. And we were getting pretty darn close to overranging on some of these connections, which is quite unusual to deal with. So how did we fix all of this? So our obvious answer is to do what they didn't do in the first place and to add pulsation control. We performed pulsation analysis on it afterwards and determined that for those, for the bottle half waves, the things that are shaking the whole side of the unit, a baffle would indeed be effective, as we described earlier in the presentation. We said that CNOs, CNO, by the way, the abbreviation is cylinder nozzle orifice plate. So we use abbreviations like that, like BIO, bottle inlet orifice plate, COO, cooler outlet orifice plate. It's just something we do to save space. But those orifice plates, when placed right at the cylinder nozzles, that's where they're most effective because closest to the source of the pulsations. So we figured that putting these orifice plates right next to the cylinders are going to kill those high frequency pulsations, and those acoustic natural frequencies will disappear. So what about the shell mode on the suction bottle? We determined that for the discharge bottle, the orifice plates would be effective because it was indeed an acoustic resonance. But on the suction bottle, it had nothing to do with acoustics. So the orifice plates are not going to help it. The baffles are not going to help it. It appears to be caused by the inherent forces of the compressor. However, the baffle can serve a second purpose. Those baffles are welded directly inside of the shell. So when you weld it in the middle of that bottle, it's acting as a stiffener. So we'll shift the mechanical natural frequency upwards if we install the baffle. This was the first time in my life I have ever recommended a baffle for mechanical purposes rather than acoustical. Really strange to see. So some commentary on this as I kind of wrap it up is that I spent 95% of this presentation talking about all the problems and just the last slide talking about the solutions. There's this huge contrast between the complexity of the problems that you can cause when you don't implement very simple preventative measures. And it's just a reminder of the importance of following industry best practices when designing machines that are thousands and thousands and thousands of horsepower. If you were to go back in time and to before I ever stuck a sensor on the unit, I could have told you that, hey, my recommendation to you, the operators, is going to be put in some orifice plates and put in some baffles. And indeed, that's the first thing I said to them after the first hour or so of testing. Are you guys okay with us cutting out these bottles, taking it, welding in a baffle, getting it pressure tested and sending it back? Just prepare yourselves for that. So these outcomes they're predictable, but being predictable isn't good enough when someone is putting their engineering stamp on it. You have to convince, I say you have to convince 3 people. As the analyst, you have to convince yourself of what's going on in the field. You have to convince your technical reviewer back in the office that you know what's going on. And you have to convince the customer that your proposed solutions are going to work. And it's very important to be thorough in these analyses so that you can kind of parse between the different phenomena and solutions that are needed. An example of this is developing a very sure understanding of the difference between the suction bottle hum and the discharge bottle hum. When the acoustic analyst back in the office got back to me and said, hey, on the suction system, we think orifice plates are good enough. We don't think you need a baffle. It's the acoustic forces on it are fine. I need to make the judgment call of, okay, can we get away with that? And the answer to that is actually, well, we did need that baffle for mechanical reasons instead. The acoustical analysts back in the office, they won't have any way of predicting that, because their models, they're all one-dimensional, as we discussed before. It had to depend on what I picked up in the field to make that call. So some lessons learned, and this was kind of geared towards my office when I presented it, but I think there's some good points in here for everyone as well, is just to remember that there are phenomena which typical models don't predict. I'm sure all of us in this room have had an example where we've had to go to some maybe in-house or third-party analysis where you're modeling something. And as the saying goes, all models are wrong, some models are useful. So you kind of have to recognize the limitations of what your specific modeling techniques are. In this case, typical pulsation and mechanical analyses, they're one-dimensional. You're not going to predict 3D shell modes in most common models in any company unless you specifically ask for them to screen to it. I'd also add that most models become less accurate beyond about 150 hertz or so. That's about as much as I would trust a 1D ANSYS model. So you can't model it up to that frequency. And even if you could, your accuracy wouldn't be the best in some of these cases. I'd also make a comment on how boundary conditions in your model can be hugely impactful and also wildly different from what you model versus what is actually built. When I model back in design, when I would model a pipe support, it was one line of code where I would input some spring stiffnesses and I'd copy and paste it because I would assume that all the pipe supports are built similarly. We give the same instructions for each pipe support. Your pipe support in the field is not a lot of code. It's a clamp, it's bolts, it's an I-beam, and it's grout. And when any of those things fail, your assumptions go out of the window. The last kind of comment is that small bore connections are a very recurring headache for us. We have seen vibration amplifications of about 20 times relative to the main line. So if you have your main line moving at 0.1 inches per second, nice and quiet, nothing wrong with that. Your small bore is moving at 2 inches per second at the same frequency, just because of that resonant amplification. Really, really nasty things to deal with, and quite annoying to test in the field as well, because you have to use glue-on sensors. And you can imagine if you have something moving real good, trying to glue something onto it it's not a very fun experience. So that's all of my presentation, just as my voice is going out. I hope I didn't drown you guys in technical information or details. I know you kind of had to learn about compressors for half an hour and then analyze one in the next half hour. So if anyone has any questions, clarifications, comments, let me know. It was excellent. It worked out. Everything worked out as we expected. So, what's that? 20 years ago. Oh yeah, it was horrible. They would intermittently turn it on only when they really needed it.
So how did that vessel ever be designed without having baffles and stuff?
Yeah, it was a head scratcher for us too, because even back then, 20 years ago, the standard we use in the industry is API, or American Petroleum Institute Standard 618. I think we're on the 5th edition now, but previously it was on the 4th edition when this was being designed. Even back then, there were guidelines for sizing of bottles, so we have no idea how this slipped through the cracks.
So when you say you're trying to convince 3 people, it was the 4th body that came to my mind, and that was the regulator, because those are pressure vessels. So
Yeah.
where would absolutely be involved?
So after you would weld something to the
Can you
vessel, you would
repeat the
have to take it
question?
and pressure test it again to get it recertified.
Can you repeat?
That
the
would be
question?
about the extent of code that we would have to deal with for the pulsation systems. Because your only other real concern with pulsation mitigation is pressure drop to the systems. So yeah, it's a good comment, because telling someone to rip out a bottle and put in a baffle, that's a massive change. Because the entire unit has to be shut down, you have to send it to a shop, get it welded, pressure tested.
Can you repeat the questions?
Build a new one. Yeah, that's the risk that they're taking. So we had to, convince them that yes, this was a necessary action. Yes.
Question online. It says, do you do modal analysis or harmonic analysis or both?
Great question. The answer is we do both. So the animation at the beginning of it was an example from a modal analysis that I did, where we calculate the mechanical natural frequencies. And then what we can also do is, the term harmonic analysis was used, but I should kind of back myself up a bit. We do an acoustic analysis first, where we predict the acoustic forces in the system. The second step is we perform the modal analysis, where we predict the mechanical natural frequencies of the system. The third step is we do the harmonic analysis, or as it's often called, the forced response analysis, where we take the predicted forces and apply it to the model to see if any of the predicted MNFs are being excited. So it's that kind of 3-step process.
Was the analysis and fix financially beneficial to the customer, or
Oh yeah.
where do you want it?
Yeah, this sort of analysis is, if I had to put my finger on it, worth maybe a couple days to a week of unit downtime, because this is they make their money by pushing gas, right? So this sort of stuff, I would argue, is very cost effective. But the more cost effective thing is to do this analysis before you build it, so I don't have to come out there.
I can see pulsation being a problem upstream, so in that
Mhm.
was it also be getting stuff, the gas pulsations in the suction?
So it's actually caused by the same reciprocating motion, and the action on the valves, it just kind of travels backwards to the direction of gas flow. On this particular system, we didn't see that happening, but it can happen.
What staggers me is I wrote had to write an advisory letter to companies about 20 years ago. Right? All these little elements coming off pipe.
Mhm.
And it's the thing that you teach in first year dynamics. Yeah. Safety advisory, because it's common sense. But the damage that it does with those cracks in the bottom of the well, the fact that the gas there is lethal.
Yep. I would say for containment breaches, failures in small bore connections are the #1 cause by far.
Yes. So the very high frequency frequencies, they must be associated with very small amplitudes also.
Yes.
So how do
Yeah.
you pick those up? The sensors are extremely sensitive.
Yeah, they are. We can probably pick stuff up reliably down to about, depending on what dynamic range we put into the analyzer, 100th of an inch per second, thereabouts.
Determine those shell frequencies or shell actions optically. Maybe we use shell lasers or something.
Using a proximity probe. The answer is yes, we can do that as well. We commonly use that for measuring deflections on rotating shafts.
Well, I think we're just starting to run out of time here, so maybe one final question. Anybody has one?
We only put so much money in the meter and then we run out.
Oh yeah.
You know, there's a big difference between what a magician does and what a good lecturer does. A magician takes something that's essentially simple and makes it hellishly complicated. And I think what we saw tonight or heard tonight was something that's quite complicated. I can't believe how clear you made that, young fella.
Thank you.
Credit to us. I really did. Now this, on behalf of our chapter, we make a donation to Operation Eyesight. So there's a little gift for you, but via the Operation Eyesight. Okay. So
Thank you.
thanks again for a wonderful presentation. Thank you.
My pleasure. Thank you.
Do you help yourself to coffee and sandwiches?
Oh, wonderful.
We should make that clear to the people who didn't join us that there was